Finally, in the characteristics of discretization, we come to the final one, which is number or the size of elements. Well, I put them together. It's because number and size of elements are quite analogous in most cases, but also I will show you in terms of location of the elements how number and size actually vary and make a difference. So in general, for every finite element analysis of a structure, we are looking for a certain solution. Now, the solution can have different kinds of requirements from our side. And for me, as an engineer who is looking for a certain prediction of a structure under loading, my main concern is accuracy, which means how good is my finite element model to give me the most accurate results. And when I talk about accuracy, then immediately there is a term that pops up in my head, which is called error. That means what level of accuracy am I going to reach? But what am I actually comparing it to get an accuracy? If it's a really complicated structure, I don't know exact values of what I am looking for. So therefore, I need to do an analysis based on my intuition, which says, yes, the structure is actually behaving in the way I expect it to behave under the current load. And if I keep running this analysis by changing just the number of elements, by refining the mesh in another way in the structure, I will be able to get to a better and a better and a better solution. But why does that happen? Let's look at this. Now, if I have any kind of a structure, let's just look at standard large plate, which is under, let's say, tension loading on both sides. So you have uniaxial tension on the plate. I can discretize this as a single element and I will get a certain solution. Now, this solution will actually be calculated at the nodes because I have defined a certain behavior of these elements. And if the behavior of this particular element is linear, then I know that there is a certain linear behavior that the element can take. Because I have enforced it. It's not like it's going to do something on its own because I didn't ask it to do anything else. So the maximum kind of deformation I can see is just a linear deformation and a linear stress and a linear strain or whatever I enforce on it. So if I have only 4 nodes at which it is doing some calculations, then I am not very certain if that's enough. So what I will do is that I will make a second iteration where I will introduce extra nodes. That means I will divide this plate into 4 elements. So I have introduced some extra nodes here, number 4, number 5, number 6 and number 7. And now what happens is that my finite element calculations are carried out at these nodes. And then I have an equivalent stress strain calculated at the center or wherever I ask. Maybe I ask close to the nodes, maybe I ask at the center of these elements. And now I have a better distribution. I have a better distribution of the stresses. I have a better distribution of the deformation because now every element can actually have a linear deformation. So I see more accurate behavior by introducing more number of nodes because calculations can be done at more number of nodes. Therefore, the extrapolation to a value of strain, to a value of stress at the center of each element can also be much better for every section of the plate. So it's best if I take this plate and I actually divide it into many number of elements. So if I mesh it up to a certain degree, I can keep improving the result because now I can have result for element here, and so on. That means I have so many results that I can actually form a trend or a certain deformation or a stress behavior throughout the plate instead of having just one value at the center. So what I did is that I started increasing the number of elements such that I also increased the accuracy of the solution while decreasing the error with respect to the expected solution. Now, simple problems like a plate under uniaxial tension can be worked out analytically. So I can get an analytical solution. I can get one. And with this, I can make a little graph here. On this graph, I will draw a line that represents the analytical solution. Say something here. For that, say I'm looking for the maximum displacement. Wherever, or on a certain location in the model. So I'm looking for a certain displacement, which will be given in millimeters. And this axis is the number of elements. It can be number of elements, number of nodes, whatever. And of course, it's also increasing in this direction. The analytical solution is of course a single one. So I have a straight line for an analytical solution, and then I start plotting results for a certain number of elements. So if I start with a small number of elements, maybe I get somewhere here, and I start increasing the number of elements. And at some point, I will see that there is no significant increase in significant improvement in the result. It sort of becomes flat. So this is the graph I make with improving number of elements. But somewhere around here, the result starts getting asymptotic, which means I'm not going to get better results than this. This basically says the number of elements are enough. And this characteristic, this behavior, where we are trying to find out what is the best number of elements, we get this behavior which is asymptotic of the result, leads to convergence studies. That means we are checking for a solution to be converged. First of all, of course, using finite elements, that means you are able to find a solution. That's one kind of convergence. And whether your solution actually converges to an expected solution is another kind of convergence. So that's the one also that we are looking for. Now, in some cases, what happens is that you don't have this analytical solution. There is no analytical solution because your problem is way too complicated. Then in that case, you just basically have to start plotting results, and you have to see where you get to a point where you have least variability in your results. So that is somewhere you have to make a choice. Yeah, with where do you stop as the maximum number of elements? And that would give you with what accuracy do you want to see your results. So if I say, okay, I have at some point here, I have quite average values, or I have quite average values somewhere here, or I have quite average values somewhere here. So I could have 3 points. I could say, okay, here is where the number of elements is converging, or here is where the result is okay, or I can also say, okay, somewhere here, and I don't care if I have such a big difference in my results. Yeah, so that's a matter of, that brings us to accuracy. So that's all a matter of choice, or rather, how accurate you want it would depend on the kind of problem you're looking at. In aerospace applications, we try to get the best accuracy possible. It's because there are humans involved, and you don't want to do a certain prediction where you know you can put lives in danger. So it is very important that your results are absolutely accurate. So that means we are looking always somewhere at errors which have to be less than 5%. And this is all theoretical. What happens when you go to the industry? You will always have safety factors. You will always be using safety factors for everything. So your safety factors will get multiplied by one safety factor, the other safety factor, and yet another one. And what you'll end up with a very conservative safety factor, which is going to make your design quite over-designed. And you will see that your error may even go up to about 30% in that case. But the industry already takes that into account by having such a conservative safety factor in place. So these are different ways of checking how many elements you want to place and why, how many is good enough, right? And that's something that I wanted to answer at the end of our talk today. And we've sort of gotten to the point. We are going to do some examples, so we'll see them in actuality with, okay, what's happening with convergence and how we are going to achieve it and how do we make sure we can get to a right value. And at the same time, we have if we keep increasing the number of elements, obviously we are reducing the size of the elements, because the structure is not going to enlarge, it remains the same. So if I want to enforce more number of nodes, I just have to enforce them at multiple locations. That's the only difference. Now finally, in any structure, you don't have to uniformly keep increasing the number of elements or reducing the size of the elements. And well, the increasing number of elements and reducing size of the elements is called mesh refinement. So we will often refer to these characteristics directly as mesh refinement. Now, coming back to the point of mesh refinement over an entire structure, doesn't have to be uniform, means that there can be selective refinement. And that is quite important for any finite element analysis, because there is, of course, a significant improvement in the error or significant reduction in the error over here when we start increasing the number of elements. But you're also making your program or your finite element analysis extremely computationally expensive. Which means you're using a lot of memory from your computer to run the analysis, but at the same time, you're also spending a lot of time carrying out the analysis. So if I have a very large structure, a more complicated problems, a lot of interactions in it, a lot of difficult contact situations, difficult loads, then I'm going to make the problem more and more complicated and hence more time consuming. That's not a very smart way to make a model or to do a finite element analysis. Sometimes it is unavoidable, so we need to do that, but we should try and reduce the time that we spend on analysis as much as possible. And if you are aware of these things, you will be able to make better choices as to how can I make a model much more computationally efficient. One of the methods, as I said, is selective mesh refinement. Yeah. And what do we need to take care of in that sense? Now let's look at a simple example of let's do a small plate, and I'm going to put in a little notch here. So it's a V notch at the center of the plate. And let's assume that it has a tension loading on both sides and the load is of the same amount. This is lying right at the center. So first of all, the first step in reducing my computational expenses or making it more efficient is to actually apply symmetry and get rid of this part. So my first step would be to say, okay, I have a notch. I'm going to reduce the plate by half. I still have the same load acting on it. And now I have some new boundary conditions that are acting on this side. And the rest, everything remains the same. Yeah. Now I have to start meshing it. I have to discretize these parts. Now there's something you have to know about discretization and corners. Actually, stress calculation at corners. Now, if you remember from basic mechanical engineering or some kind of stress analysis that you did, if you have a corner which is as sharp as this one, then you always end up with a stress concentration at this area. These areas are also called as singularity points. Because once you start calculating the stresses at this point or the stiffness matrices, you will see that you can't do an inverse because it's a singularity, it's a corner, and therefore you see stress concentrations developing here. Now, one of the ways to actually check whether it's actually a singularity or it's just like high stresses, you keep increasing the number of elements at these corners. You keep refining the mesh, and what you will see at these kind of corners is that no matter how much you refine the mesh, no matter how many elements you add, your stress always keeps increasing. It never asymptotes. There's no way this happens. And this means that there is a stress concentration. And therefore, there is a reason why in every mechanical design you make use of fillets. And that is getting rid of all the stress discontinuities, all the stress concentrations that happen at structures. So if you look at this model, this particular model here, you will see that there are these corners. Yeah, there's a corner here, there's a corner over here. So you can always expect a stress concentration point to exist. So the best design is actually to make it rounded, to have a certain radius so that there is no stress concentration point. But it's a notch, so we don't do that. So that's something that we are expecting. So we know that there will be a certain increase in stress in these areas, and it will always remain of this nature. It's not going to become asymptotic. So we have to then think about meshing properly. So what we do is first we just say, okay, let's just make a uniform mesh. Let's just mesh it simply like this. And we see that here in this element, you see a lot of stress concentration. And that's not very good for us. Yeah, of course, these are 2D four-sided elements. And what we do is we say, oh, there's a stress concentration here, so I'm going to start improving my mesh. So I add more elements. I add more elements and I add more elements everywhere. I keep reducing the size of the elements uniformly. The stress here improves up to a certain point, but does not asymptote. It keeps increasing anyway. Yeah, and that's something we are sort of expecting to happen. But here in these areas, not much changes. You have a stress, you get to a point where you have the maximum stress that you are going to achieve, and then you stop. But to make sure that the entire model is the best in terms of accuracy, we are increasing the mesh everywhere. So this area increase of mesh doesn't make any sense after a point, because there the stresses have settled, they have distributed correctly, and they stay that way. So the best way to think about meshing in these cases is to consider biased meshing. And this biased meshing is a kind of selective refinement. What we want to do is that in areas of significantly high stress concentration, we can make high number of elements. But the rest of the place, we don't have to make such high number of elements. Please don't go by my lines here. They should all be quite uniform. So I'm sorry about that. This is just bad drawing. But you see that here, I wanted a slightly more refined mesh, and I could make it by just biasing the number of elements that I need to have in that area. Of course, you have to do it really smartly. There are different ways of doing it, and you'll try a few things, you'll fail, you'll learn more. But this is a thing that comes with experience. Okay, so always make sure that there are round cutouts around these edges, load introduction points. You always need to have more and more refinement to have a better result. We'll do a couple of examples now, so you'll be able to follow them much better. Finally, I want to talk about size of the elements in general. Size of elements. Not size of elements in a global sense, but size of elements in a local sense. If I have a two-dimensional element, a rectangular element, and I have a certain width and a certain height, what kind of elements are ideal? Because I can have elements that look like this, the elements that look like this. There can also be elements that sort of look like this. So which ones are actually good? Which ones are correct to use in a finite element analysis? Well, the best one is this one, where A is almost equal to B. Because the best aspect ratio you want to use is 1. Sometimes you can get away with stuff like this. So if you say the aspect ratio of your element is roughly about 5, it's still acceptable. But elements like these, you should try and avoid. Well, this one also sort of okay, but this one absolutely not. Because you have certain points inside your element, like Gauss points, where all these characteristics are being calculated apart from your nodes. So you see that the variation across the length can be quite large in some cases, especially close to concentration points, especially if you have elements that look like this around here. For example, this element would do really badly in this area, and so will this element, because the aspect ratio is quite large. So these are things you need to take care of while using meshing. In the next two videos, I will pick up a couple of examples, one one-dimensional and one two-dimensional. We will stick to meshing for the two-dimensional part, but for the one-dimensional part, we will also check some analytical results and go on to look at some characteristics such as convergence.